Welcome back to AI Codecast, and today we're diving deep into a classic coding problem.
Yeah,
It's called the house robber problem.
it's a good one.
It is. It's a really good one, so get ready.
Buckle up.
Yeah, buckle up, because we're going to break down this challenge and explore different ways to solve it.
We're going to go from like the really basic,
Brute force.
brute force, and then we'll get into some really elegant techniques.
Dynamic programming.
Yeah, dynamic programming, exactly.
So to set the scene,
Yeah, let's set the stage here.
imagine you're a robber
Okay,
and you're presented with a street lined with houses,
right?
each containing a certain amount of cash.
I like where this is going.
Your mission, if you choose to accept it,
Of course I choose to accept it.
is to figure out the absolute best way to rob those houses to maximize your loot.
All right, so I'm looking for the big bucks, right?
The big bucks, yeah.
Okay.
But there's a catch.
Uh-oh.
You can't rob adjacent houses.
Oh, that makes sense.
Right.
Wait.
Well, because that would trigger the alarm system
Oh, okay.
and an abrupt end to your heist.
Yeah, no police, thanks.
No police. Right, so it's not just about grabbing the biggest stacks of cash from each house.
Okay,
You need a plan.
a strategy.
You need a strategy, exactly,
Okay.
to navigate this constraint and come out with the maximum possible haul.
I'm intrigued.
So I know some of you listening might be tempted to just try every single combination of houses.
Yeah, that's my first thought. Just try all of them.
Seems simple enough, right?
Right. Yeah.
But that brute force approach can get
Messy.
very messy,
Yeah.
especially when you have a lot of houses to consider.
Yeah, because like how many combinations would that even be?
So if we have, let's say, non-houses on the street,
Okay, on houses.
a brute force approach would involve checking 2 to the power of n combinations.
Oh, wow.
Yeah,
That's a lot.
that's a lot of possibilities to sift through, and it quickly becomes computationally infeasible.
Infeasible, yeah. Like my computer would melt.
This grows larger.
They would just be like, no, no thank you.
Yeah, so brute force is
The window.
out the window. We need a smarter way.
All right, so what's a better way?
Where do we even begin?
Yeah, where do we even begin to look for a more efficient solution?
So let's step back for a second
Okay,
and think about the structure of the problem itself.
okay.
At each house,
Mm-hmm.
you have a choice.
Okay.
You can either rob it
Okay.
or skip it.
Rob or skip, I like it.
And this choice impacts the choices you can make at the subsequent houses.
Yeah, I can see that. Like, if I rob this one, then I can't rob the next one.
Exactly.
So it's like a chain reaction.
Yeah, there's this sort of cascading effect
Right.
where each decision kind of ripples through the rest of your choices.
That's a good way to put it. It ripples.
So that's where the concept of recursion comes in.
Recursion, okay, I've heard of that, but remind me.
So we can break down this problem into smaller,
Subproblems.
similar subproblems.
Okay.
Imagine you're the robber.
Hi, and I'm back in the game.
You're standing in front of a house.
Okay.
You have 2
For
options.
rob or to skip?
Rob it or skip. Yes, we've been over this.
We have.
But this time, imagine that for each option,
Mhm.
you have a little helper
A little helper.
who can figure out the best way to rob the remaining houses, following the same rules.
Okay, so if I rob this house, my helper is going to tell me the best way to do the rest of the street.
Exactly.
Yeah?
And they have to follow the same rule. So they can't rob adjacent houses either.
Oh, that's crucial.
So if you choose to rob the current house, your helper is going to tell you the best way to rob the rest of the street.
Okay.
But they have to start 2 houses down.
2 houses down, right? Because
Yeah.
we can't rob the next one.
Exactly.
Got it.
And if you choose to skip the current house,
Huh.
your helper will tell you the best way to rob the rest of the street,
Okay.
starting at the next house.
All right, so they have a little bit more freedom.
Exactly.
Okay, I like
So they were breaking down the problem into these smaller, identical pieces, and then we're combining their solutions to get the best overall strategy.
Ah, okay, so we're like delegating the problem to these little helpers.
Yes.
That's pretty cool.
That's the essence of recursion.
All right, recursion.
And it actually leads us to
Dynamic programming.
a technique called dynamic programming.
Knew it was coming.
But we'll delve into that in the next part of our deep dive.
Okay, can't wait.
So we've gone from this brute force approach that could overwhelm our computers
Yeah, melt them down.
to this elegant, recursive idea
Elegant, I like that word.
of breaking down the problem into smaller pieces,
Manageable piece.
more manageable pieces.
Yeah,
So listeners,
Yeah.
if you're even remotely interested in algorithms
or optimization.
and optimization,
Who isn't?
don't miss part 2,
Where we unlock the secrets.
the secrets of dynamic programming.
Ooh, I love secrets.
And we'll see how it can crack this house robber puzzle.
Wide open.
Wide open.
Welcome back to AI Codecast.
We're back.
Last time, We laid the groundwork for tackling this house robber problem.
Yeah, we did.
We talked about brute force,
Uh-huh.
that it wasn't a great approach.
Yeah, it gets really messy.
And then we hinted at the power of recursion.
Yes, we did.
So are you ready to unlock the magic of dynamic programming?
I am ready.
All right.
Let's do it.
So from what I gather, dynamic programming is all about solving problems by breaking them down into smaller subproblems and storing the results of those subproblems to avoid redundant calculations.
Dear God.
So it's like being really organized. It's like having a thief who's got a notebook,
Okay.
and they're keeping track of all the best ways to rob different sections of the street.
So they don't have to recalculate everything every time.
Yes, exactly.
That's a great analogy.
So how do we apply this to the house robber problem?
Yeah, how do we do that?
Well, let's think back to our recursive approach.
Okay.
Remember those little helpers?
Yeah, the ones that helped us rob the houses?
Right. They told us the best way to rob the remaining houses.
Uh-huh.
So we had those two choices, right? Rob or skip.
Right, skip, yeah.
So this time, imagine instead of those helpers, we have a table.
A table.
Let's call it max loot.
Max loot.
And in this table,
Yeah.
each entry is going to represent a house.
Right.
So if we had, let's say, 5 houses,
Mhm.
our table would have 5 entries.
5 entries, okay.
Right. And each entry is going to store the maximum loot
Oh, yeah.
that we can get from that particular house.
Okay, got it.
So how do we fill this table up?
Yeah. How do we fill in the table?
Well, we start with the easy stuff.
Okay.
What's the maximum loot we can get from the very last house?
Well, we'd have to rob it.
You got it.
So the maximum loot would just be whatever is in that house.
Exactly.
Okay.
Now, what about the second to last house?
The second to last house?
We've got 2 options there.
We can rob it.
Rob it.
Or skip it
Skip it.
and rob the last one. And we just pick whichever one gives us more money.
You got it.
Okay.
So we're starting to build up our max loot table, right?
Right, okay.
We fill in those last 2, and then we just work our way back.
Okay, so we're going
Backwards, house by house.
house by house.
And for each house,
Yeah.
we're going to consider those 2 options.
Rob it or skip it?
Rob it or skip it, and
Yeah.
we pick the option that gets us the most loot.
Okay, so we're using
Using what?
those results
Yeah,
of the smaller problems to solve the bigger problem.
exactly.
So we're kind of building our solution up
Building it up.
from the ground floor, one house at a time.
You got it.
Okay.
That's the beauty of dynamic programming.
It is pretty beautiful.
By the time we get to the first house,
Yeah.
our table's going to have the answer we're looking for.
Awesome, okay.
But,
I'm thinking.
what do you think?
This table,
Yeah.
it's going to take up a lot of memory.
Yeah, that's true.
What if we have like 1,000 houses? Yeah, that's a lot of memory.
That's a lot of entries in our table.
Mm-hmm.
So remember how at each house, we really only needed information from the 2 houses before it?
Yeah, we didn't need the whole street.
Exactly.
Just those last 2.
So
Yeah.
what if instead of a table,
Yeah.
we just use 2 variables?
Wait, 2 variables. Instead of that whole table,
Ditch the table.
and we'll still get the same answer.
We will.
My mind is blown.
It's all about optimization.
Optimization, okay.
We just need the most relevant information.
Okay.
And those 2 variables, they hold the key.
All right, so how does this 2 variable magic work?
All right, so we start at the end of the street.
Okay.
Just like before, we're going to have Rob next, plus it's going to be 0.
0, okay.
Because there's nothing left to rob after the last house.
Right.
And rob next,
Yeah.
that's just going to be the value of that last house.
Okay.
Because that's our only option there.
So it's kind of like those base cases?
It is. It's just like our table.
Okay.
Now here comes the cool part.
Okay, the cool part.
We move backward through the houses one by one.
One by one.
And for each house,
Yeah.
we're going to calculate this new value. We'll call it current max.
Current max, all right.
That's the best we can do at that house.
Okay.
So to calculate current max,
Mm-hmm.
we've got our 2 options. Rob the current house or skip it.
Okay, same as before.
If we rob it,
Yeah.
current max is going to be the value of that house plus rob next plus own.
Right, because we can't rob the next one.
Exactly. And
Mhm.
if we skip the current house,
Yeah.
current max would just be rob next.
Okay, so we're making the same choices as before,
We are.
but we're just using these 2 variables instead of looking at the table.
Exactly.
Uh.
And then we just swap our variables.
We swap them.
We swap them.
Okay.
Rob next plus own becomes the old rob next, and rob next becomes our newly calculated current max.
Okay, so we're just
There's like sliding a window,
sliding a window, yeah.
1 house back.
Okay, I like it.
And by the time we hit that first house,
Yeah.
Rob next is going to have our answer.
It's going to have the max loot.
The maximum loot.
Wow, that is
Right, cool.
really cool. So we get the same answer as our table,
We do.
but we use way less memory.
Way less memory.
That's amazing.
It's all about optimization.
So we just had to
Yeah.
pay attention to what we actually needed.
Recognize those patterns,
Absolutely.
and boom, we've got a much better solution.
I'm thoroughly impressed.
I knew you would be.
This is
Elegant.
so elegant.
Inefficient.
And it all came from that one observation about the two preceding values.
That's all it took.
So we started with this complex problem,
Yeah,
explored all these different approaches,
I did.
and now we've arrived at this really sleek solution.
We've come a long way.
We have
So listeners, stick around for the final part.
part 3,
We're going to recap
all the key takeaways.
and maybe explore some other variations
Oh,
on this house robber problem.
I can't wait. Welcome back to AI Codecast for the final part of our deep dive.
We made it.
We did. We made it to part 3 for the house robber problem.
It's been quite the journey.
It has. So we started with brute force,
Yeah, not a great approach.
and then we moved on to recursion,
Much better.
and then finally dynamic programming
The best.
with all its clever optimizations.
It's amazing how much more efficient we made it.
Right. From that massive table
Yeah, who needs all that memory?
down to just 2 variables.
2 variables, that's all it took.
I feel like we've really uncovered the essence of dynamic programming here.
We have.
Breaking down problems, storing results.
Building up to the best solution.
But before we wrap up,
Yeah.
is there anything else about dynamic programming in general
Let me think.
that you think our listeners would find valuable?
You know, the house robber problem,
Yeah.
it's really just a gateway
To bigger and better things?
to the whole world of dynamic programming.
Oh, so it's not just about robbing houses.
Mhm.
No, not at all.
There are real-world applications for this.
Absolutely.
Like what?
Well, think about any problem
Okay.
where you need to make a series of decisions
Mm,
to, say, maximize something
maximize. Okay.
or minimize something.
Minimize. All right.
So let's say you're packing a knapsack.
Knapsack. Okay.
You want to fit as much as possible.
Right. As much valuable stuff.
Exactly. Or maybe you're managing a project.
Mm-hmm.
You need to allocate resources.
To different tasks?
Yeah. Or even finding the shortest path.
Oh, like on a map?
Exactly. Like a GPS.
Wow. I never realized how useful dynamic programming could be.
It's everywhere.
It really is. I'm starting to see it everywhere now.
It's like a new way of thinking about problems.
It is. It's like a new lens.
You start to see those patterns.
The overlapping subproblems.
Exactly. And then boom.
You get that efficient solution.
Every time.
Well, this has been
It's been fun.
an eye-opening deep dive into the house robber problem and dynamic programming.
I hope everyone learned something. I know I did. I've definitely leveled up my problem-solving skills.
That's what we like to hear.
Any last words of advice for our listeners?
Don't be afraid to experiment.
Okay.
And remember,
Yeah.
even the toughest problems
Mm-hmm.
can be broken down into smaller pieces.
Manageable pieces.
Exactly.
And you might surprise yourself.
You never know what you might come up with.
That's a great point.
So keep coding.
Happy coding, everyone, and we'll see you next time on AI Codecast.